Remember rational numbers, they're just fractions. So rational functions are of the form g of x over h of x, where g of x and h of x are polynomials. And the interesting thing that happens with these rational functions is that they have undefined values, where the denominator is set equal to 0. So the domain is the set of real numbers except where these problem values happen, except for the values of x where the denominator would be 0. So vertical asymptotes are of the form x equals a, where a are the values that make the denominator 0. And horizontal asymptotes, y equals b, are horizontal lines where the function gets closer and closer. So the value of f at x approaches these values as x approaches infinity and as x approaches negative infinity. So special asymptotes we have to be on the lookout for. We have to understand how to find a horizontal asymptote. If they have the same degree, you can just divide the leading coefficient of the numerator by the leading coefficient of the denominator, and that will give us the equation y equals b. So it will give us the horizontal asymptote. If the denominator's degree is greater than the numerator's degree, then y is just going to be 0 for the horizontal asymptote. And kind of case 3 is the oblique asymptote. We don't have to worry about that too much, but we have to understand if the numerator's degree is greater than the denominator's, you're going to end up with an oblique case. To find the x-intercept for a rational function, you're doing the same as always, setting y equals 0 and solving for x. This could involve factoring. And to find the y-intercept, you're going to set x equal to 0. Positive intervals are where the value of f at x is greater than 0, and negative intervals happen when f at x is less than 0. Increasing intervals occur when f at x is increasing. So as you're going from left to right across the page, the graph is rising. And decreasing intervals is where happens when f at x is decreasing. So as you go from left to right across the page, f at x is going down. So let's take a look at an example. So we're going to start with sketching the graph of g at x, which is 2x over x plus 1. The first thing we want to look at are the problem values that would make the denominator 0. So x plus 1, if it was to equal 0, that would mean x equals negative 1. So x equals negative 1 is the value of the vertical asymptote, and that also gives me my domain. So x is an element of the real numbers such that x cannot be negative 1, because that's where the function itself is undefined. Horizontal asymptotes, well, we're looking at when x gets really big or really small. So as x goes off to infinity or negative infinity, what happens to g of x? A little shortcut that we have for this is to check the degree. The degree is 1 on the top and the bottom, and because these match, we're just going to divide the leading coefficients. So 2 divided by the 1 on the bottom, so y equals 2 would be the horizontal asymptote that it would tend towards. You have to be a little bit careful because in all cases, the range is not going to be y is an element of the real numbers such that y cannot be the value of that horizontal asymptote. But for most of the simple cases that we're looking at in this course, it will be. You can actually have a graph pass through a horizontal asymptote in the center and sort of just tend back towards it as x goes to infinity or negative infinity. The x and y intercepts, of course, are easy here, 0, 0, because if you put a 0 in the top of our fraction or in the numerator, 2 times 0 makes the whole fraction 0. And vice versa. If 2x over x plus 1 is set equal to 0, then x would be 0. Positive intervals, so we have to do this once we draw a graph. Negative intervals, same thing. Increasing and decreasing intervals, we're going to come back to once we've created our graph. So now I'm going to go down so I can make a little sketch. And the first thing I want to do is just put on those asymptotes. So x equals negative 1. Would be here. And y equals 2, I believe, was the other one, so we'll put that about here. Perfect. And we also know that 0, 0 is on this graph. So what we're going to do, we're going to assume that our y equals to our horizontal asymptote is a boundary. Again, we can't always assume that because it could cross it, but we will get the curve going closer and closer to y equals 2 and closer to x equals -1 on the left side and passing through 0, 0. This is not the whole graph. So what we need to do is pick another test point that's to the left of the asymptote x equals -1. So let's just remind ourselves the function itself is 2x over x plus 1. And we already know that 0, 0 is a point on our graph. But let's say we picked -2 as our x value. That value is lower than -1 to the left of -1 on our graph. So 2 times -2 over -2 plus 1. We end up with -4 over -1. And this comes out to +4. So I have another point on the graph, -2, 4. And I can put that, so that was -1, -2, -3, -4. So I am going to, oh, sorry, I got -2 and 4 actually would be up here. And so now I have another point, and I know that the graph is going to pass through that point and tend towards the asymptotes on either side. So I would always suggest, so that you don't forget that last piece, that you go back and double check that you have a point on there as well. Okay, so now we can talk about positive and negative. So this graph is positive or above the x-axis for that piece, and it's also above the x-axis for this piece, so when it's greater than 0. So when it's less than -1, and the way we're going to write this is to say when x is less than -1 and when x is greater than 0, that will happen. In terms of negative intervals, x is only negative between -1 and 0. So it's below the x-axis is what we mean by negative. And this graph is always increasing except for at the value of x equals -1. Because as you move from left to right along the x-axis, the graph is going up and the graph continues to go up. So it's never decreasing. It's always increasing except for at -1. So what we can say is when x is less than -1 and when x is greater than -1. Or you could say x an element to the real number such that x can't be 1 if you want to write it that way. There's also interval notation that you sometimes see. So I could write, for example, the negative interval. You might see recorded in the answers as -1, 0. That means x is between -1 and 0, not a point -1, 0.